So now let's look at field strength. So what's the formula for field strength for a spherical planet? So now we're not thinking about the field generated by a point particle, but it's the field generated by a spherical planet. Again, a lot of these things I've drawn a planet already, even in our previous examples, rather than a point particle, just because it was clearer to see. But it's clear exactly the same stuff works just as when we were pretending we had point particles, with the same caveat as we had in our last video. So it's exactly the same as before, providing that we're outside it. So if this is our setup, we've got a planet of radius r, mass of m, and we're a particle that we're wanting to find the field strength at a distance of r, a radial distance of r from that sphere. Where again, clear r is the centre, it's from the centre of the sphere, not from the surface. And then our formula is exactly the same as before. We can immediately write down this is always true that the gravitational field strength is just the force experienced by this test mass divided by its mass, so it's the force per unit mass. And so if then for r bigger than capital R, that is to say for r a distance from the centre that's greater than the radius, that is to say we're not inside the sphere, we have that it's exactly the same formula we had last time, which is to say G is capital G m over r squared, where G is our field strength and this G is Newton's, is the universal constant of gravitation as before. And m is the mass of the planet as we've got here. But this only works for r bigger than capital R bigger than the radius. If we're less than the radius, we actually have a different formula for field strength. And you might ask why? If we're pretending all the mass is centered at the center of the sphere, does it matter if we're slightly inside of that? If it's acting as if all the mass is here, does it matter if we're here rather than here? And the answer is it does, because if you think about it, when we're here, we've got mass. We're actually at the center. We're basically on a circle of a sphere of a smaller radius. We haven't got all the mass here as we do here between, like for instance here we've got the mass of this entire sphere between us. When we're here, we've only got the mass of this between us and the center, and so the formula is different. It's actually quite significantly different. And it produces a very different characteristic, because you might think, well, if we've got this formula where it's over r squared, what happens is r goes to 0? Does g just go to infinity? But because you've got this spherical sphere, the answer is, as you're going in, yes, I mean, you would here you supposedly have got this r squared thing going on, but actually as you're going in, you've got less mass, and so as r decreases past r, so for r less than so as r's decreasing for r less than as capital R, you've got less mass because of the sphere affecting you, because you're going inside the sphere now, and so you get a very different formula, and we'll just touch on that very briefly in a moment.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.